Hello, my name is Paul Greenlaw. I am a 5G solutions architect with Comdex. As part of my 5G Talk series of videos, I will provide an overview of private 5G and describe why it's a great network architecture for the enterprise. If you like this video, don't forget to hit the like button and subscribe to the channel. The topics I will be presenting in this video are definition of a private 5G network, highlights of the service-based architecture, quick overview of the network functions. I will then go deeper into the enterprise building blocks to implement a private 5G solution, covering the hardware, network, orchestration, and management aspect. I will provide an overview of some cool use cases for artificial intelligence in a private 5G network. I will cover the three GPP defined deployment models. I will present an overview of Open Radio Access network implementation, and I will conclude with an overview of how artificial intelligence can help in the security domain of a private 5G network. A smart network that can observe, analyze, and react is ideal for digitizing an industrial campus and enhance its operations and efficiency. With a private 5G network, an enterprise can integrate Internet of Things, artificial intelligence, data analytics, and automation to optimize processes in manufacturing, logistics, and maintenance. The technology allows for seamless connectivity of devices with real-time monitoring, predictive maintenance, and data-driven decision-making. Industries range from logistics to energy and utility companies. With private 5G technology, there is great potential for the automation of industrial plants. Using robots in manufacturing and production can boost its efficiency, reduce labor cost, and minimize errors. Examples of such industries include automotive, electronics, and pharmaceuticals. Private 5G also enables the enterprise employee to be digitally integrated in the workplace by taking full advantage of 5G smartphones, tablets, wearables, and software for real-time collaboration and communication. The result is a more productive, efficient, and safer workforce. This concept is called connected worker, and it can be implemented in any enterprise that relies on real-time communication for optimizing tasks and ensuring worker safety. Enterprises in general can leverage private 5G for condition monitoring, predictive maintenance, remote configuration, remote maintenance, and autonomous mobile robots. These are implemented via smart assets, which are part of the Internet of Things ecosystem and are used in various industries such as manufacturing, logistics, and agriculture to enhance operational efficiency and enable data-driven decision making in the enterprise. Private 5G is a technology for the enterprise that delivers capabilities that others can't. A well-implemented 5G network adapts to the requirements of a multitude of evolving enterprise use cases, which are defined by coverage, mobility, forwarding capacity, latency tolerance, and resiliency. There is no other technology today that can do this, and the nature of the architecture allows for flexible deployment models such as a fully standalone option and hybrid and full hosted options that leverage the support of a service provider. It also supports high data rates for extreme mobile broadband and massive machine-to-machine communications, up to 20 gigabit per second downstream, and ultra-low latency for critical machine-to-machine communications down to the millisecond. From a technology perspective, it can be said that 5G is exponentially better than 4G. It has been optimized for greater capacity and lower latency in the RAN. It features a service-based architecture that provides a very clean approach for configuration and discovery of all services in the network. The service-based architecture also allows an operator to commission new elements and remove elements from the network with minimum or no disruption to the network. It introduces network slicing to allow partitioning of the private 5G network to a group of devices. This may serve requirements for users wanting dedicated network resources with specific traffic needs under certain circumstances. For example, an enterprise may have a need to divide their network based on business domains like employee mobile service, business applications, and critical applications. Another example is a service provider dedicating network resources to enterprise users, providing a fully hosted private 5G network or a partial one. 5G offers a more granular quality of service approach for differentiated services. A user may have different defined IP flows per PDU session, and each can be provided unique treatment. The architecture also breaks down control and user planes, which allow for optimal placement of network functions and more flexible scalability of resources. This means that media functions like the user plane function can be placed closer to the users to minimize latency, while keeping the control functions like session manager function and access management function in a more centralized location. The separation of control and media functions also enable the scaling up or down of control and media functions independently from each other. The support for microservices software architecture and cloud native implementation is one of the best attributes of 5G. What this means is that common off-the-shelf hardware is used and an orchestration layer is present to monitor in real time all the CPU, memory, and storage resources in the environment to be able to deploy all the microservices. It should be noted that microservices makes up a 5G network function. There is high resiliency because most microservices implement N plus K redundancy and are distributed well by the Kubernetes orchestrator over the hardware. When hardware or software elements fail, the orchestrator redeploys the affected microservices automatically. The 5G network can be integrated via API interfaces to third-party systems in a secured manner, opening opportunities for evolving use cases. As an example, an artificial intelligence system with a security algorithm could be used to continuously perform analysis of data collected from different network elements via the API and determine the feasibility of a security breach and provide the proper measures. Another use case is the use of API to automate the creation and removal of a network slice. Let us take, for example, a scenario in which congestion overtakes the network. A mission critical slice may be dynamically created by an automation system to ensure a particular group of users are given access to the resources. Traffic associated with these users essentially is given more priority over traffic from other slices. A private 5G network supports a services-based architecture. Taking a deeper look, what this means is that there is a very organized process for registering services into the network and for discovering the services that are available. This was not possible with prior generations of mobile technology. The network repository function is responsible for this coordination. The players of a private 5G network are either service consumers or service producers. The network functions can have both roles. The access mobility function handles the mobility management of the users. The session management function is responsible for the session control. The authentication server function handles the authentication and authorization. The policy control function is responsible for policy definition and control for quality of service. The network slicing selection function manages the slices. The user plane function handles media forwarding and policy enforcement, and the user data repository stores the user database information. The 3GPP body of standards made a decision to use REST API as the language for communication among consumers, producers, and the network repository function. As shown in the diagram, registration procedure is used by a producer to advertise the services it offers. The discovery procedure is used by a consumer to find out who has the services it needs. And the request procedure is used by a consumer to communicate directly with the producer for a service it needs. In a typical private 5G solution, there are several building blocks that are needed to make it smart with the ability to observe, analyze, and react. Let's look at the building blocks in detail, starting with the IP backbone. This is the existing enterprise IP network made up of routers, switches, and firewalls, which today provide access to all existing users. Once the private 5G network is deployed, it will provide access to packet data networks, which may be remote networks, the internet, remote campus sites, or service providers, and it will also support a larger ecosystem of devices. Hardware resources and additional networking equipment will be needed to deploy the solution. Common off-the-shelf equipment such as Dell or HP servers will integrate to the network and provide the connectivity for the 5G radio access network and the packet core. The initial deployment of all network functions will be the responsibility of the orchestrator and network management system. During the planning phase, a network architect captures all the resource requirements for the microservices that make up each network function and the corresponding anti-affinity rules which have all the redundancy requirements. The orchestrator builds a model of each network function required for deployment and captures the configuration in Helm charts. This is what the Kubernetes control aspect uses to deploy the network functions. All microservices are deployed as pods, which is the minimum unit of deployment in Kubernetes. Once all network functions are deployed, the Kubernetes control aspect will monitor each pod, and it will automatically redeploy it if it dies due to a hardware or software issue. The configuration aspect of the network functions is done via the network management system or command line interface, and once the deployment of the 5G private network is completed, the network management system will handle ongoing management of faults, configuration changes, accounting, and performance. A device management system is also required to handle the configuration, software updates, and management of the devices. Furthermore, a private 5G environment can integrate to other systems to support a multitude of use cases. Artificial intelligence systems, for example, can provide the means to analyze valuable data from the 5G network and offer capabilities such as optimization and self-healing. By continuous processing of data collected from the 5G network, it can identify issues in real time, such as congestion in the core, signal and degradation in the RAN, and apply the proper measures. Predictive maintenance. By continuous processing of data collected from the 5G network, it can predict equipment failures or performance degradation before they occur by analyzing data from various sensors and network devices. In turn, it can make necessary changes to the environment. Quality of service management. It can monitor and optimize quality of service for different services and applications on the private 5G network. It can prioritize traffic based on application requirements, ensuring low latency, high reliability communication for mission critical applications, while efficiently handling less critical traffic, resource management, and load balancing. It can analyze network usage patterns and dynamically allocate network resources based on demand. This enables efficient load balancing, ensuring that critical applications always have the required resources, while non-critical applications don't overconsume resources. Security and threat detection. Private 5G networks are often used in sensitive industries. Artificial intelligence systems can monitor network traffic patterns and identify unusual or suspicious behavior indicative of cyber attacks or security breaches. It can help detect and respond to security threats quickly, protecting the integrity and confidentiality of network data. The 3GPP working group has defined a few deployment models for private 5G in Release 16. The slide shows 4 deployment options, starting with the fully standalone deployment, which is also referred to as standalone non-public network deployment. In this scenario, all network functions are located within the enterprise premises and isolated from the service provider. All control and media traffic stays local. Optionally, communication between the enterprise and the service provider can be implemented via a firewall and serves as the demarcation point. This connection can be used for accessing public services. The enterprise has the responsibility for operating its private network and for the configuration of the services attributes. Alternatively, enterprise devices can subscribe directly to the service provider to access its services with a dual subscription. Optionally, a connection can be leveraged to access enterprise services via the service provider. There is a deployment option where the radio access network is shared. In this case, the enterprise and the service provider network have a mutual agreement and share part of the radio access resources, while other network functions remain segregated in the enterprise premises. All control and media traffic related to the private network stays within the enterprise, and the public traffic portion is transferred to the service provider. The private network gets its own dedicated non-public network ID. It is possible to have an optional connection between the enterprise and the service provider via a firewall, and it is also possible to configure additional base stations that are only accessible to enterprise users and devices. Then we have the option of a deployment in which the enterprise and the service provider network share the radio access resources, and the 5G control tasks are performed by the service provider. In this scenario, all control traffic is handled by the service provider, while media traffic remains local. This scenario can be implemented by means of network slicing at the service provider network, providing isolation of core resources from other slices. Another approach is to use the 3GPP defined access point name, which identifies where to route traffic, allowing differentiation between enterprises. The enterprise can also decide on a fully hosted deployment model where all T-control and media traffic are handled by the service provider, but the hosted network exists as a completely isolated private network dedicated to the enterprise. A service provider can implement this by means of network slicing or by defining an access point name to the enterprise. In this scenario, enterprise subscribers are, by definition, also service provider subscribers. Since all data is routed via the service provider network, access to public network services and the ability to roam can be implemented easily in accordance with the agreement between enterprise and the service provider. In all deployment models, operations and management is a key aspect to consider. Enterprises managing the fully standalone private 5G network have local access to their network functions and can strive for the implementation a unified management system with the flexibility to manage the network functions lifecycle via a cloud orchestrator system and the fault configuration, accounting, and performance monitoring aspects via an element management system, which is typically provided with the purchased vendor product. For the deployment models that involve the service provider, access to the network functions can be achieved via secured API exposure. But in this case, the level of management and control will be dictated by the service provider. In summary, the deployment approach of enterprises significantly impacts how they operate and manage network functions and access critical network and service data, particularly when the 5G private network coexists with the service provider on the same infrastructure. Selecting the appropriate deployment model will depend on factors such as how much control over the equipment and operations is desired, the level of expertise available, the network footprint, and the business model. Open Radio Access Network is an initiative involving several organizations and industry bodies, primarily through collaborative efforts. The two key ones are the Open Radio Access Network Alliance and 3GPP body of standards. Their main objective is to define the functions that should make the architecture for the 5G radio access network and standardize the functionality of the entities and their interfaces. The implementation internals of each function remains proprietary to the vendor manufacturer. From a functional view perspective, the architecture decomposes the traditional baseband unit into a centralized unit and a distributed unit. It also defines the interface specifications between the centralized unit, the distributed unit, and the radio unit. From a software perspective, these units are implemented as containerized network functions based on microservices and deployed over cloud technology. From a hardware view perspective, this means that the technology is hardware agnostic. Vendors can implement their software over common off-the-shelf hardware and leverage Kubernetes and container runtime systems to deploy and manage the microservices. From a resource management perspective, it normalizes the way radio resources are managed via the RAN Intelligent Controller, and it also allows third-party software to integrate and introduce optimization capabilities. Furthermore, ORAN provides a framework for orchestration and lifecycle management of the containerized network functions. Let us look at some of the benefits and challenges of Open Radio Access network implementation. The benefits include by the decomposition of functions into centralized unit, distributed unit, and radio unit, it opens the field for deployment options. The standardization of the architecture into functions and interfaces, it allows operators to select best of breed option and promotes competition and quality. There is also reduced in hardware cost because you can use common off-the-shelf hardware. The adoption of microservices and cloud-native technology gives it greater scalability, like what the Packet Core is capable of today. There is also greater reliability due to the distributed and redundant nature of microservices. Furthermore, as cloud-native functions, there is better visibility and control over the RAN resources. There is also support for integration with third-party software to leverage best-of-breed optimization capabilities. But there are also challenges. Vendors, for example, may have difficulty agreeing to the interpretation of standards, potentially delaying product and feature development. There is also the need for complex testing activities before certifying multi-vendor interoperability, impacting time to market. Also, some level of customization is required to onboard a third-party containerized network function to a vendor's cloud system. The operator also may face changes in the integration. Cloud customization and configuration will be necessary for multi-vendor deployments, and testing is also an additional activity that operators will need to consider when implementing a multi-vendor open radio access network solution. As private 5G networks continue to evolve, operators need to be vigilant about security to protect their network, data, and critical operations. In addition to implementing the security capabilities that 5G offers, such as authentication, authorization, identity concealment, location concealment, and encryption, and security best practices such as regular software updates for devices and the implementation of security policies and network firewalls, it will be necessary to complement with an artificial intelligence security approach for greater efficacy. Earlier in the presentation, integration with artificial intelligence via API interfaces was explained. Here is how it can help specifically with the security of a private 5G network. Detecting anomalies. It can identify unusual patterns in network traffic, alerting operators to potential attacks or security breaches. Behavioral analysis. It can differentiate between legitimate and malicious traffic by analyzing the volume and rate of incoming requests, helping to mitigate distributed denial of service attack situations, responding to real-time events. It can automatically respond to threats in real time by rerouting traffic, blocking malicious IP addresses, or adjusting network parameters to absorb a distributed denial of service attack on demand. Predictive analysis. It can use machine learning to predict potential breaches based on historical data and current network conditions, allowing for proactive measures. Automating incident response. In the event of a breach, it can automate incident response procedures, aiding in containment and mitigation. If you liked the video, please hit like and don't forget to subscribe. Thank you for your attention.